35 and 37? All right, we'll do one of them. 37? Okay. Look at the classroom. So today, our topic is going to be about something called rate of change, which we discussed already is connected to slope. But today we're talking about it in terms of a new philosophy, a new system, which will make things different. It'll involve implicit differentiation for some of it. It's good. So let's take a look at number 37. See that implicit differentiation in action. And here we go. 37. Cruciform. X squared y squared minus 9x squared minus 4y squared equals 0. Okay, let's do it. So there's a few ways I could do this problem. And so I will showcase like some of the paths we could take to do this. Just remember, my long-term goal is to get y prime isolated. So the more I can do to get y isolated, the better it can be in the long term, because it will help me find y prime. So example, I could start this problem by isolating y, at least as far as I am capable of without having to split the problem apart. So I will showcase kind of like an optional first step, but then I'll go back and do this like a standard problem just so you can see both. So an optional first step. I could move this piece over, give me x squared y squared minus 4y squared equals 9x squared. Factor y squared out. So that x squared minus 4. And then divide. So I'd end up with y squared equals 9x squared over x squared minus 4. Now if I take a square root, I will end up with two answers, a positive and a negative. So I have to do two derivatives instead of one. I'm not going to do that. I'm going to do it implicitly from here. Again, I could have done it from the original problem, and I would have been fine. I would have been golden. This one just happens to be a slightly different version of it, which will still work. And so it's an optional way you could try to rewrite this problem to get to your solution a little differently. Because again, all of the algebra rules are available to you. You may take any approach you wish to solve these kinds of problems. Your goal is y prime. Whatever steps necessary to do that, we need to get y prime by itself. So my point is that negative 4, comma, 2 radical 3. So I can choose to either go from here, the original problem, or here, this newer version of the problem. Both should give me the same solution eventually. But because that top one, I can already see I'm going to have a product rule, which is going to lead to me having y prime inside of a multiplication problem. So I'm going to have to do some boiling and then some factoring to get y prime by itself. Like I have to be able to look at this long term and say, what's going to be best for me 5 steps down the road. I look at this a lot like chess. The people who are good are not going to necessarily win every time, but they're going to see better ways to get to the approach. They're going to see better ways to set it up, better ways to get to an easier spot so they can win easier. I think of this as a problem where I can get to this point and be like, okay, well, that's simple power rule on the left-hand side. It's a quotient rule on the right-hand side. I can do both those without too much issue. So I'm going to use this form. Let's do it. Y squared equals 9x squared over x squared minus 4. Left-hand side, ddx of y squared over 9x squared over x squared minus 4.
2y times y prime.
Which to get y prime by itself is simple. I just divide by 2y. So that's really straightforward. On the right-hand side, I have a quotient rule so that I have the top and the bottom. The top is 9x squared. Its derivative, t prime, 18x. The bottom is x squared minus 4. So the bottom's derivative would be 2x. All right, so I do the quotient rule now.
9x squared
9x squared
times 2x
times 2x
minus x squared minus 4 times 18x.
You have the right idea. I think these two are backwards. Remember, typically low d high minus high d low. Okay. So Let me see if I can. Cheating. Not cheating, not trying. Look at that. You didn't make a single mistake. Okay, over the square of what's below. So x squared minus 4. Okay. Now to get y prime by itself, I would divide both sides by 2y, but that's easy to do. So again, like long term, this path is significantly easier because I was able to isolate the y's to one side, so isolating the y prime is that much easier. So y prime would be equal to, I'm not even going to simplify the top or the bottom. I'm just going to leave it the way they are. Remember, my goal is not to get the slope iterating function y prime, it's to find the slope at this specific point, negative 4 to radical 3. So 9x squared times 2x over, so I divide the 2y over, so 2y ends up on bottom, times x squared minus 4 squared. Now, everywhere there's an x, I'm going to plug in negative 4. Everywhere there's a y, I'm going to plug in 2 square root of 3. Let's do it. So, y prime at negative 4, 2 square root of 3. Now, this is probably going to be nasty. Again, I will simplify what I can, but otherwise my goal is just to make sure to get it as simple a form as I can. X squared, so that'd be negative 4 squared minus 4. 18, that's negative 4. Minus 9, negative 4. Squared times 2, negative 4. All over. 2y, so 2 squared 3. Times negative 4 squared minus 4 squared. Okay. Here's simplify what I can. Alright. On top. Negative 4 squared, this should be 16. Minus 4 should be 12. Times 18 times negative 4. That's the same as 8 times 9, that's negative 72. Minus, let's see, 4 squared is 16. 16 times 9, that would be 144. Times, here negative 4, negative 8. Okay, on bottom, 2 times 2 radical 3 would be 4 radical 3. Times, negative 4 squared would be 16. Minus 4 would be 12. 144. Yes, good. Okay, let's figure out the top. Alright, this is some big numbers. I don't know if I can do this by myself. Thankfully, I can do some cheating here. Okay, cheating. This becomes 6 times negative 144. So double negative will make this positive. Oh, you're about to see some nasty tricks. On top, I get 288 over 4 radical 3, 144. Check my work if you need to. That's right. 144 and 288 cancel, leaving a 2 on top, 4 radical 3 on bottom. 2 and 4 cancel, leaving 1 over 2 radical 3, or radical 3 over 6. Woo! Flex. I can't handle. For mental math stuff, rewriting in the same forms with 144s is really helpful because I can treat it like a variable. I have 6 times this thing minus 8 times that thing. So I get negative 2 times that thing. Cheating. The problem said to find the tangent line, I do believe, for 37. What is the tangent line, right?
Yep.
So now I've got the slope, last step. Y minus y1, 2 squared root, equals m, greater than this, x minus x1, plus 4. Here's my solution. Woo! All that So, implicit differentiation. We take a derivative of both variables with respect to a single variable. So we take the derivative of x with respect to x, that causes standard rules to apply. The derivative of y with respect to x causes y prime to appear in the problem itself, which we then solve for manually, allowing us to get a solution. Now, for today, we take this one step farther. Today's a big day. A beautiful day. A glorious day for the Empire.
Oh, yes.
Yes. Okay. So far, we've taken the derivative with respect to x for everything we've done. We've, on occasion, switched to a different variable, but only if that variable matched the problem. So we took the derivative with respect to t if the problem had t in it. Or we took the derivative with respect to z if the problem had z in it. Cool, great, amazing, awesome. Okay. Now we're going to take this one step farther. Because in many realistic applications, the variables in question are not the only variables in question. Most physics-based applications, for example, that deal with location, use x and y values. However, what matters for many of the time is time. Example. A standard function indicating the position of a cannonball being shot out of a cannon. So, picture in your brain a beautiful cannon shooting the cannonball.
Oh, it's a black thing.
Yay.
Diagrams. That had to be thought.
Okay. Now, this cannonball will perform a nice parabolic shot, meaning it will have a formula, something like the y value is equal to x minus h squared plus k with an a up front. Right, standard mathematics. However, if I want to talk about this spot specifically, there's a couple ways I can do that. I can refer to the x value, this location on the ground. So if I'm underneath it, I would look straight up and see the cannonball right there. I can refer to it by the y value, so how high it's at. Or I can refer to it by how long it has been in the air. We call it time t. So in this case, we have an equation with x's and y's in it, but this equation could also be in reference to t. Where in this case, the x value depends upon t. The y value depends upon t. This is common in most physics-based applications. And as a sort of reminder from way back when, much of calculus was designed specifically to solve physics-based problems. So now we're going to look at some equations today, looking at rate of change as an implicit idea with respect to t. Most of your homework questions will sound a lot like physics questions. You will have equations that have x's and y's already in them. You aren't allowed to use either of them. You have to use t. How does this change anything? Not much. The implicit rules are still going to apply. The standard rules are still going to apply. The only issue is the standard rules, you're not going to have t in the problem. Everything has to be done implicitly. Let's take a look at this equation. As our first example. A simple one. A simple quadratic, if you will. Y equals 2x squared minus 4x plus 3. In a physics-based application, there is a hidden variable t. X is based on t, y is based on t, the location, at time t. So how do I take this derivative? To do so, I would take this function and do a derivative using all the standard derivative rules, but instead of d dx on the outside, we're going to use d dt. Now, we do not know how t is going to interact with y. We do not know how t is going to interact with x. So we will end up with two unknowns. Do y dt and dx dt. Two unknowns. Unknowable, unobtainable values. Here we go. Now for this problem, I'm going to do it in Newton notation. So just like on before, when we practice these, I'm going to do it with each component with d dt. Like so. Let's look at what happens to each component. This left-hand one, d dt of y. This becomes dy dt. What is the derivative of a variable by itself? So the derivative of x is usually 1. The derivative of y, usually y prime. The derivative of d is going to become dy dt. The derivative of 2x squared. Well, the 2 is obviously a constant, so it'll pop out. Now we do a power rule. But it's a power rule with respect to t, the same way we did with respect to y's earlier. So this becomes 4x times dx dt. The derivative of the 2x squared is the same as normal, it's 4x, but because I'm taking the derivative of x with respect to t, I would have a dx dt up here. Because I don't know how x and t are interacting, so I have to have a variable there. It's an unknown. Continuing forward, over here, again, the 4x acts like a normal 4x. I take the derivative. The derivative of negative 4x would become negative 4. The derivative of x becomes dx dt. So you can see in here how each component has a match. 2x squared becomes 4x. Negative 4x becomes negative 4. It has a matching component. But each one creates this new dx dt or dy dt, depending on which variable you're dealing with. And if there were t's in this problem somewhere, the t's would be treated like normal, like with an x. Just do the same derivative with respect to t. The derivative of the constant, t, d dt for 3 is 0. Derivative of the constant is always 0. So let's think back to how we talked about this terminology at the very beginning. What does this say? How is 2x squared changing with respect to time? 2x squared is changing by a factor of 4x, while x changes with respect to time. Negative 4x changes with respect to negative 4, while x changes with time. Y becomes the change in y with respect to time. Each component has its own derivative, now with respect to t. And again, this is primarily used in physics-based applications. I'm going to pull up your homework here in a second. You're going to see there are physics-based applications for many of the problems. The reason being is the understanding of how these variables has to work together now is reliant upon these values. And now in a problem, you could have x be a number that's given to you. The rate of change, dx dt, could be given to you in the problem. dy dt could be given to you in the problem. And you could solve for any or all of these. Let's look at a problem. This is just a standard way to take a derivative using the variable dt in substitution for x or y. Now let's take a look at an actual problem. Again, not a huge difference. These ones are like the ones we just did, but notice how we could be given dx dt. What does that mean? Well, anywhere there's a dx dt, I just plug it in. I could be given when x is 4. Anywhere there's an x, I replace it with 4. So again, notice how you can be given and asked to find different things. I could be asked to find dy dt, so the change in y with respect to time, when the x value is 4, when the rate of change of x is 3. I could be asked to find when is the x value changing with respect to time, when the x value is 25 and the change in y is 2. Again, how the time changes matter, because time is now considered to be the constant in every physics problem. Time moves at a linear pace. It goes from 1 second, 2 seconds, to 3 seconds, to 4 seconds, to 5 seconds at a linear pace. And everything else moves around it. X moves with respect to time. Y moves with respect to time. As you go farther along, you start to see more problems that are based upon physics application. Find the rate of change of the distance between the origin and a moving point on the graph of y equals x squared plus 1 if dx dt is equal to 2 centimeters per second. What does it mean? Unlike with standard problems, you may have to pull some problems from previous classes. Pull some equations from previous classes. Examples. This question is asking about the distance. So at some point in time, we're probably going to use a distance formula. 13 asks about the radius of a circle is increasing. Find the rate of change of the area. So we're probably going to use the area formulas. Other problems can ask about things like angles of the sides of a triangle, radius of a sphere. How is its volume changing? These problems are some of my favorites because they pull in pieces from Algebra 1, Algebra 2, and geometry and say, you don't have the formulas. Find them. Use them to find things like dV, the change in the volume with respect to time. dD dt, the change in distance with respect to time. But I can't answer the change in volume with respect to time unless I know the volume formula and how to find its derivative. I can't answer the distance formula to change the time, rate of change, unless I know the distance formula and how it's changing with respect to time. Over the next few days, these are our goals. And as we go farther along, they do get slightly more complicated, but you notice that for the next few days, you'll see a lot of similar terminology. We'll be taking notes over some of the terminology we use and the primary process, the primary 3 steps we can follow to get to our solutions every time if we can read our problem. So let's start with the easy stuff. Let's see. Number 1 is an assigned problem, so I will do number 2. I don't know what's going on next door, but it sounds cool. I think she just likes playing music during her class. I don't know. Ironically, if it gets picked up by my microphone too much, YouTube will flag it for copyright infringement. Which I find hysterically funny. What? Number 2. Y equals 4, parentheses, x squared minus 5x. I want to find, for part A, dy dt when x equals 3 and dx dt equals 2. For part B, I want to find dx dt when x equals 1 and dy dt equals 5. Now, I will point out a couple of things. You notice on some problems they give you both x and y. On other problems they only give you x. If for some reason you need to find y, how could you do it? Algebraically? That seems like a lot of work. I'd probably rather just, plug it in. It's arithmetic. Algebra people just claimed it for themselves. That's actually good. Okay, let's do it. Part A. Ironically, both of these have the same first step. So I'm going to do it to the side here. Find the derivative with respect to t. Let's do it. I have 4 parentheses x squared minus 5x. I'm going to begin the problem by distributing. Y equals 4x squared minus 20x. Step 2. Taking derivative with respect to t. So I take this function, d dt, of the function. Now, just like with before, when we talked about implicit differentiation, I'm going to start by doing and showing every single step. Distributing the ddt, and then taking derivative of each piece of ddt. But once you get a little more comfortable with it, we do not have to do this middle step here. Okay? Left-hand side. What is the derivative of y with respect to t? dy dt is actually all we need. Because dy dt is y prime. The derivative of y is y prime. Equals the derivative of 4x squared with respect to t. What?
dx dt ax.
So always think the derivative of the original thing times the derivative of the variable itself. So the derivative of 4x squared is, of course, 8x. Times the derivative of x would be dx dt. The derivative of y would normally be a 1 if it's with respect to y. I multiply that by dy dt. The derivative of 20x with respect to t.
20 dy or d dt.
20 dx dt. So what's A asked for? A asks for, we want to find dy dt when these two conditions are met. When x equals 3 and dx dt is equal to 2. So I go to this problem. Everywhere there's an x, I plug in 3. Everywhere there's dx dt, I plug in 2. Let's do it. So everywhere there is a dx, I plug in 2. Everywhere there is an x, I plug in 3.
So wouldn't it be 8?
Say again?
Wouldn't it be 8?
What do you mean?
Because it'd be 48 minus 40.
Oh, you're just yeah, sorry. I thought you were saying like something up here should be 8. I'm like, what? What? Ah! Yes, the answer is 8. Which means, how is y changing with respect to time in these two instances? The slope for y is 8 with respect to t. So how y is changing over time is it changing 8 units per second. That's another way to think about it in physics terms now. Y is changing 8 units per second. Second part asks for dx dt. Now, I have dy dt already in. So what I can plug in, when x is 1 and when dy dt is 5. Now, I can either do some simplifying at the beginning or at the end. It doesn't really matter too much. I'm going to go ahead and do it at the end. Everywhere there's dy dt, I replace with 5. So, 5 equals dx dt times 8 times 1 minus 20 dx dt. Okay, it's a little bit foreign for us. We've only used these for a total of 20 minutes. dx dt is a variable by itself.
So you can do 8 minus 20.
So I can do 8 minus 20. And what is 8 minus 20? Negative 12.
Then divide by negative 12.
Ow, yes. Divide by negative 12 and we will find dx dt. Remember, dx dt acts like a variable. So it'd be negative 5 over 12. That is our solution. Dx dt, dy dt, they are just a variable. Well, what does this mean? When the x value is 1 and the y is changing at a rate of 5 units per second, the x will be changing at a rate of negative 5 over 12 units per second. Let's put this in other terms we discussed. Part A. What was our solution for part A?
8.
8. dy dt was 8. Let's put that in perspective. The change in y with respect to time was a positive 8. In other words, the rate of change for y is 8 units per second. That's 8 dt. Furthermore, because it is 8, the y value is going up. That's positive. So it's going up 8 units per second. Consider part B now in that thinking. When the x value is 1 and the y value is changing at 5 units per second, the x is changing at negative 5/12 units per second. So as weird as it seems, the x value is moving to the left 5/12 units per second. Or 5 units per 12 seconds, whatever you want to do. Which seems weird because normally x always moves from left to right. But in physics, you can do a lot more complicated things. You can describe more complex scenarios, like a cannonball being shot from right to left. In that case, the only way to rationalize that is the x value has to change from left to right, or from left to left. And again, just like with the ways we talked about how y prime is the slope of y, how y values are changing. dy dt does the same thing, but with respect to the time it's changing. Dx dt represents the same thing with respect to the time it is changing. We got something number 4 as well? Let's do it. So these problems will give us practice on standard derivative rules, implicit derivative rules, algebra rules, geometry formulas, algebra formulas. Ooh, this will be a fun week. I can already smell it. That's the smell of sweet, sweet victory. Number 4. As you guys are looking at number 4, what kind of formula is this? It is a circle. Hey. A. Find dy dt when the following is true. X is 3. Y is 3. Sorry, Y is 4. And the x dt is 8. So think about this. How to put this in physical terms. Okay. If I wish to draw this circle, think of a mathematical formula not as just a picture, but a picture changing with respect to time. If I want to draw this circle, described by x squared plus y squared equals 25, like think about it. I could run at a constant rate to draw my circle. But even as I do that, the x values are going to change differently than the y values, even though I am physically moving at a constant rate. Okay? As I start at the top, I start off by going more to the left than anything else. So my x values are going negative, while my y values are hardly changing at all. As I go farther along, I get over here. The y values start changing a lot, and the x starts changing at all. Originally, the x, so dx dt, the change in the x is going to be a negative number. The change in the y, up there, dy dt, is a negative number because it's going down over time. When I get to here, my dx dt is switching from negative to positive. Because I started off going to the left, and I'm reaching my apex, and I'm switching over to the right. My dy dt, still going down. even though, again, remember, I drew this at a relatively constant rate. Time was constant. How each piece of this is acting is completely different. And these are different than my slopes at these points. That's the other key detail. My slopes are different. At this spot up here, my slope would be 0. My dx dt, because I started off going counterclockwise, was negative. My dy dt was 0. When I get over there, okay, my slope is undefined. My dx dt is defined by, in this case, from negative to positive, so it would be a 0 value, an undefined value. My dy dt, clearly negative, is going down over time. So I now have 3 things I can talk about. The general slope formula, dy dx. Dy dt, the change in the y values only. Dx dt, the change in the x values only. Fine. To actually answer our problem, I'll start this one. You can finish on your own if you wish. 2x do x dt plus 2y dy dt equals 0. And once we define dy dt, knowing those 3 things, so I put those 3 things in. X is 3, y is 4, dx dt is 8. 2 times 3 times 8, 48. 2 times 4 would be 8, dy dt equals 0. Move the 48 over, 8 dy dt equals negative 48. So y dt is negative 6. So think about it. Think of my circle. So beautiful circle, thank you. 3, 4 will be right around here. The slope is clearly negative. Dx dt is a positive number, dy dt is a negative number.
Delilah Richard, you're needed in the office. Delilah Richard, please come to the office.
There's one other fun little detail as you guys back up. Dy dt over dx dt is the actual slope. Think about it, these will cancel. We can do y over dx, which is y prime. Cool concept. We'll continue the discussion tomorrow. See you guys then. More assignment will be due Friday.